NASA's James Webb Space Telescope will see the formation of the earliest galaxies following the Big Bang, but in order to do so, its equipment must first get extremely cold, really cold. On April 7, Webb's Mid-Infrared Instrument, MIRI, which was developed in collaboration with the European Space Agency, ESA, and NASA, attained its ultimate operational temperature of less than 7 kelvins, -447 degrees Fahrenheit, or -266 degrees Celsius. MIRI, along with Webb's other three instruments, first cooled off under the shadow of Webb's tennis court-sized sunshield, with temperatures decreasing to around 90 degrees Celsius, -298 F, or -183 C. Cryocoolers driven by electricity were necessary to achieve temperatures lower than 7 Kelvin. Last week, the team achieved a particularly difficult milestone known as the pinch point, which occurs when the instrument moves from 15 kelvins, -433 degrees Fahrenheit, or -258 degrees Celsius, to 6.4 kelvins, -258 degrees Celsius, -448 F, or -267 C. MIRI Cooler team member Annalyn Schneider said, "The MIRI Cooler team has put in a lot of hard effort into establishing the method for the pinch point." Schneider works at NASA's Jet Propulsion Laboratory in Southern California, which is home to the MIRI project. The crew was both excited and worried as they prepared to participate in the key exercise. Final result, a perfect implementation of the technique, with cooling performance that was considerably better than anticipated. Due to the fact that all four of Webb's equipment detect infrared light, which has wavelengths that are somewhat longer than those that are visible to the human eye, the low temperature is required. Infrared light is emitted by distant galaxies, stars shrouded in dust cocoons, and planets outside of our solar system, among other things. However, other heated items, such as Webb's own electronics and optics technology, have the same effect. The infrared emissions are suppressed by cooling down the detectors of the four devices as well as the surrounding gear. MIRI detects infrared wavelengths that are longer than those detected by the other three devices, requiring it to be much colder than the others. Another reason Webb's detectors must be kept at a low temperature is to suppress what is known as dark current, which is electric current generated by the vibration of atoms within the detectors themselves. It is possible to fool detectors into thinking they have been struck by light from an external source by using dark current to simulate a real signal in the detector. Those erroneous signals have the potential to drown out the true signals that astronomers are looking for. Considering that temperature is a measurement of how quickly the atoms in the detector are vibrating, lowering the temperature results in less vibration, which in turn results in less dark current being produced. To detect longer infrared wavelengths also makes it more sensitive to dark current than the other instruments, which means it must be kept colder than the others in order to completely eliminate this impact. The dark current increases by a factor of approximately 10 for every degree Celsius that the instrument temperature rises. Researchers launched a series of tests as soon as MIRI achieved its freezing point of 6.8 kelvins to ensure that the detectors were performing as intended. The MIRI team examines data detailing the instrument's health in the same way a doctor would check for signs of disease, and then gives the instrument a series of orders to determine if it is capable of doing the duties assigned to it. Scientists and engineers from a variety of organizations, including Northrop Grumman, which developed the cryocooler, and NASA's Goddard Space Flight Center, which oversaw the integration of MIRI and the cooler with the rest of the observatory, have come together to achieve this significant milestone. According to Mike Ressler, project scientist on MIRI at the Jet Propulsion Laboratory, "We spent years rehearsing for that moment, running through the commands and tests that we did on MIRI. It was a little bit like a movie screenplay in that everything we were expected to accomplish was written down and practiced. When the test results came in, I was overjoyed to learn that everything had turned out precisely as predicted and that the instrument was in good working order." There are still a number of obstacles that the team must overcome before MIRI can begin its scientific mission. As soon as the device reaches operational temperature, the team will begin to collect test photos of stars and other well-known objects, which will be used for calibration as well as to assess the equipment's functioning and performance in general. In addition to these preparations, the crew will also be working on calibrating the other three sensors, with the goal of providing Webb's first science photographs this summer. In a statement, Alistair Glass, MIRI instrument scientist at the UK Astronomy Technology Centre, ATC, in Edinburgh, Scotland, said, "I am immensely proud to be a member of this group of highly motivated, enthusiastic scientists and engineers who have come together from across Europe and the United States. Despite the fact that we are in the midst of a trial by fire, it is already clear to me that the personal bonds and mutual respect that we have developed over the course of the past years will see us through the next few months and enable us to deliver a fantastic instrument to the worldwide astronomy community." Once again, thank you for taking the time to view our newest update video on the James Webb Space Telescope, JWST. We hope to see you next time. Take care.